Hello, my name's Ben. I'm a software engineer at Instacart, and I've been working here for about 5 years. Before that at Microsoft, before that at a whole bunch of other startups for the past decade at least. And I've divided my time in my career mostly between mobile and back-end development. Today, I want to talk about experimentation, how Instacart developed the ability to run tens of thousands of experiments for millions of shoppers and customers with billions of assignment decisions every day. I'm going to talk about the system we built, which is called Roulette. I'll spend a few minutes describing how we built it, why we built it, and how it works. I'll spend a little more time talking about how the things that made it really work well on the back end didn't work very well on mobile and how we had to turn the system kind of upside down to fix that. At the end of this talk, I'm hoping to leave you with some ideas for developing your next system and for how to bridge the gap between the systems that back-end developers build and things that mobile developers need. So let's begin. To set the stage, Instacart is, what is it? It's an online grocery technology company. We were founded in 2012, went through Y Combinator, grew a whole bunch, and now we're available to 95% of the households in the US and Canada. So on top of the delivery business, we also run ad services for over 6,000 consumer packaged goods brands. So what is experimentation? What does that mean here? So experimentation can mean a lot of things. I like GitLab's definition the best here. They call it a way to validate and measure improvements to a digital product against particular goals. So experimentation is critical for the way we operate. Whenever we're facing a product design question or a business question, we want to be data-driven. We want to be informed. And experimentation is the best tool we have for informing ourselves. Obviously, you can't measure everything that matters, and you can't use experimentation to replace critical thinking and your own judgment, but it remains an essential tool. So how do we get here? Well, how did we arrive at this place where we needed to build the system that I'm talking about? In the beginning, in 2012, as most companies at the time did, we had a single Rails app with a single Postgres database on Heroku. We had a rudimentary experimentation system built on an open source library called Flipper, and honestly, it worked really well until around 2016. Around then, we'd outgrown Heroku, moved to AWS, and our monolithic code base became too unwieldy to keep working, so we refactored it. One app became 2, became 4, and even more. And each app got its own copy of an experimentation system. Each app got its own team with its own mission. And as those teams progressed, their needs diverged, and the systems they used to run experiments diverged too. Around 2018, we had settled in with about 4 major monolithic applications and a whole constellation of smaller services, each with their own mutually incompatible experiment systems. Like we couldn't even run an experiment across 2 of them at the same time. And this state of affairs continued until around early 2020 when we started the Roulette project. So what is Roulette? Roulette is an assignment engine. Let's talk about some terms here. So what is an assignment engine? That's a weird term. An assignment engine is a system that assigns users to a variant of an experiment. When I talk about experiments, I mean specifically multivariate experiments in which groups of users or a cohort are shown a variant, a different user experience, and then we track the behavior of those users through time to see what impact to the business those different user experiences might have had, or as this is commonly known, A/B testing. Except in this case, we often have more than just A and B. So when we kicked off this project, we had to decide what we wanted it to do. So obviously we wanted it to be a single source of truth because the problem was that this is pure chaos. Like if we wanted to run an experiment from a customer placing an order all the way through a shopper fulfilling it, we're a host. There's no way we could have done that. So we needed a single source of truth with a single service vending the same experiment data to everybody. We wanted it to be correct, which sounds kind of trite to say, but some systems do compromise on consistency or correctness in order to prioritize availability. We can't make that trade. We have one user has to see one variant for one experiment. Otherwise, our experiments lose their power. And since it's a new service, we wanted it to be fast. Couldn't introduce too much latency. One problem that we had was that even though we couldn't do experiments end to end, we had a lot of experiments running. Some of our most common endpoints might have dozens of experiments running at the same time. If we had a separate network call for each of those experiments, we would have completely blown our performance budget for the whole request already just an experiment assignment. So we had to be smarter than that. So how do we hit that target? So it turns out that the cheapest network call is no network call, and the cheapest assignment that we can do is no assignment. We had our assignment service do nothing except for tell all of our applications what experiments were in force. And all of the assignments were actually done in process in the applications that needed them where and when they needed. So this actually had some important implications. So if all of our applications are generating assignments by themselves, they're not coordinating with anything, that means assignments need to be a deterministic process. They have to have the same answer every time. Secondly, the fact that we're not consulting some central authority for assignments means that there's no state. And that means that assignment is not only deterministic, but it is a pure function. It can only consider the experiment definition itself and whatever attributes of the user are relevant to that experiment. So this is what we built, and we shipped it, and we found out that not only did it meet our latency goals, it actually crushed them. We watched the tail latency at the P90 for our experimentation systems. All the existing ones dropped from like tens of milliseconds to single-digit microseconds. Great success. It introduced a new problem, which was, since our applications are the ones doing the assignments, like how do we keep them informed? Like how do we keep them up to date? It's actually an important problem. We'll talk a little bit more about that later. First, I want to talk about the roulette data model, how it works and why it works, because it's interesting. So the central data structure in roulette is called a feature definition, or feature for short. The salient aspects of it has a name, like it's a unique name to identify the experiment, has some variants that it knows about, and it has rule sets. What's a rule set? A rule set has rules, which are predicates about a user, like is the user an admin, or is this customer shopping at a particular set of retailers. They define what segment of traffic the experiment applies to. And finally, they have variant weights, like what proportion of the experiment population should get a particular variant. So when a prospective cohort member satisfies all the rules for a rule set, then they are assigned a variant according to those weights. And how this assignment process happens is key to the system, and it's worth spending a little bit of time talking about. So the nature of variant assignment in experiments is that it must be unpredictable. Like if you can predict the variant of a user before you actually assign it, you introduce bias to an experiment, you erode its or completely eliminate its predictive power. So cool. Most of the time that's easy. You just slap a call to random and it's fine. But the problem for us is that as a distributed and stateless and uncoordinated system, we can't actually use a random number. Otherwise, nobody would agree on the same assignment. So we had to be a little smarter. What could we do? Well, backend devs are probably nodding along here. They see where it's going because, as in so many other problems, the answer involves hashing. Hashing is, of course, the process of converting some arbitrary data into a fixed width byte string with the properties that output is usually unique to the input, and crucially, it's unpredictable from the input. So it's randomized, in other words. There are thousands of hashing algorithms out there you probably know, like SHA-1, SHA-256, MD5. We settled on one called XXHash. It's small, it's super fast, it's high quality, it's available everywhere, basically. And so with this, we can take something unique about an experiment, like its name, and something unique about the user, like an ID or an email address, combine them and get a randomized number that is nonetheless deterministic. And this is enough to get predictable randomized variant assignment. Like a simple thing to do is just take that number, mod the number of variants you have, and boom, you've got a variant ID. Almost. So for one, if you're thinking about modular bias, yeah, we're thinking about this too. This is not the final solution. And it's not the final solution for another reason. As we just talked about, variants have weights. Like they're not just evenly distributed. We need to be able to accommodate 5% of people go into control, for example. So how can we do that? Is there any way we can adapt this technique for weighted variants? Well, it turns out that yes. One simple thing we could do is just pad the list of variants. Like say A, B, and C variants have weights of 2, 1, and 1. Well, we can just keep the same algorithm, but just put A in that list twice. That by itself is enough to get predictable, randomized, and weighted variants. But it's still not quite enough. Because while this works in isolation, the fact is experiments exist in time and they change over time, particularly when you take into account optimizations like multi-armed bandit. I won't talk too much about how those work, but the salient aspect of those is that bandit and other techniques involve looking at experiment data as it comes in, analyzing and identifying which variants are performing better than the others, and directing a greater share of traffic to the winning variants. And in this way, you minimize the loss or maximize the gain from any particular experiment. Well, that means we need to be able to change the weights dynamically. And that poses a problem here because in this algorithm, changing the weights is destabilizing. It re-randomizes everybody's variant, which effectively destroys your experiment. So what we want is, if we're going to, emphasize variant A, de-emphasize variant B, the only motion that we want to see users going from B to A. Can't do that with this approach. It just fundamentally won't work. So what can we do? I think some backend engineers probably see where this is going too, because this turns out to be a classical problem in storage and networking domains. And the classical solution is something called consistent hashing. There are a number of different algorithms out there. The one we settled on is called weighted rendezvous hash. For me, this is like a desert island algorithm. It does so much with just a very small amount of effort. It's fast, it's simple, and really useful. I won't get into too much detail about how weighted rendezvous hash works, other than to say it sort of adapts existing hashing algorithms. So we can take XX hash and plug it into this formula and get a score adjusted by weight. If you want to learn a little more about it, I would really encourage you to go follow the link on this slide, because it's an easy read and really enlightening. Okay, so now that I've talked a little bit about how roulette works and why it works, let's talk about what the system looks like. What does it look like? It looks like this. So this diagram shows all of the major components of roulette as it exists today at Instacart. Up here is a database-backed RPC service. It has a small number of components do a small number of things. It's basically a very simple wrapper around our source of truth, which is a single Postgres database that holds all experiment definitions, past and present, because key thing about that is that it's append only, which will be a little important later. And next we come to the heart of the system, which is the backend client libraries. These are much more complex than the backend itself because they do the work. Most of their complexity is in the assignment evaluation algorithm, which I'm not going to get into right now. But the libraries are interesting from a scalability perspective. Remember that they have to hold all of the experiment set in memory and keep it up to date. How they do that dictates a lot of the backend's performance and even its design. So we had a couple choices here. Mobile developers are familiar with polling versus push notifications. Polling is when you reach out to a backend service at some cadence and say, hey, what's new? Push notifications, in contrast, are when the server itself reaches out to the clients and says, hey, I've got something new for you. Please go get it. Of the two approaches, push notifications are much more scalable. They're much more efficient. But they're also a lot harder to build, so we didn't do it. We went with polling, and it's not optimal, but it's been good enough for the past few years. So the only reason that this works at our scale, well, okay, what's our scale? Right now, we have about tens of thousands of experiments running at any given time that the libraries need to know about. So that means that our compressed data set is probably in the megabytes at this point, the tens of megabytes even. And so our libraries poll for updates every 30 seconds. If we weren't smart about this, that means we're shipping 10 megabytes to every application server every 30 seconds. And you very quickly reach a point where this is just not operable. It's too expensive. It's too slow. We're wasting too much bandwidth. We're wasting CPU resources. So this is where the append-only nature of our database comes to the rescue. Because every change to our database results in inserting a new row with a new auto-incremented ID, we have a very natural high watermark that we can use. So we use this to introduce pagination to the API. Whenever Roulette sends down a response, it includes that high watermark with it. Clients can include that value the next time they make a request, and the server can say, here's what's new since the last time you made a request. And that actually works very well. It makes operating Roulette possible. And in fact, it made it super efficient because almost all of the responses that happened after we introduced pagination were 0 bytes, which was great. Super efficient, right? Like we can scale down. We don't need 100 Roulette nodes. We maybe need 3. But this introduced an interesting problem in the nature of bimodal responses. What does that mean? So the vast bulk of our responses were 0 bytes long, which is awesome. But a small portion of our responses were many millions of bytes. And that usually happens when an app starts up for the first time and has no experiment data at all, and it needs the whole data set. So this combined with autoscaling in a really interesting problematic way. So because the vast majority of our responses were so tiny, we could autoscale down very easily to like 3 nodes. Problem being when we lit up a major new customer internally. When the morning scale up happened, when our traffic started to spike up early in the morning as people began to place orders, we very quickly had this wave of worst case requests and a skeleton crew of Roulette servers to handle them. So this situation actually caused several hours-long outages. Eventually, we solved it by just eliminating bimodality entirely. So one of my favorite questions to ask when it comes time to design a system is, how reliable does it need to be? Does it need to be as reliable as S3? If the answer to that question is yes, the next question is, can we just use S3? In this case, the answer to both is yes. Yes, we can. So we can just keep a cache of up-to-date feature definitions in S3. So whenever a new application node starts up, instead of asking the Roulette backend for that worst-case request of all the data, it can just download it from S3. This means even if Roulette's completely down, an app can start up and have a reasonably up-to-date experiment set. And since we introduced this, we haven't had a single scale-related outage. S3 is pretty amazing. Next, I'll talk about the events pipeline just a little bit. I won't spend too much time on it, except to note that despite all the talk about statelessness of the system, the entire point of an experimentation system is to keep state, right? Like, we go to all this trouble because we want to know who saw what, when, and why, so that we can analyze their impact on the business. Like, that's the whole point. You can build this on basically any streaming platform today. Like, we've used Kinesis and Kafka at different points. They all work, and there's not much to it. And finally, we come to the newest member of the family, the mobile SDKs. Instacart is a mobile-first product, and so our mobile developers naturally want to take part in the same experimentation ecosystem as their back-end counterparts. And here is where the nature of mobile applications comes into play. So up to this point, Roulette had only ever had back-end customers. And as a consequence, a lot of our design hinged on these kind of unstated assumptions that we made about how things work. Mobile applications being so different, this posed quite a challenge to us. So what were those assumptions and how were they problematic? We assumed that memory was cheap and freely available. You can hold all this data in memory all the time without impacting your host application. We assumed that bandwidth was capacious and widely available, that we could download as much data as we need whenever we need to. Laughably untrue on mobile. And finally, we assume that services are available, that once we boot it up, we can reliably talk to anything we want to talk to whenever we want to. And if you've ever used your phone in a grocery store, you know that's not true. So what did we do about it? The first challenge we had to tackle was bandwidth usage. So we are available to 95% of households in the United States and Canada. That's a very broad geographic footprint, and mobile availability is really variable across that space. So, 5G is great, but it's not as widely deployed as we'd like. A lot of our customers are still stuck on LTE or 4G even. And bandwidth is really expensive, right? Like, customers pay by the gigabyte. And when your payload is in megabytes, it doesn't really take very many polling requests before you start hitting people in their wallets. And that's just unconscionable. Like, we couldn't ship a product that would cost our customers money that way. So right away, we hit this impasse. So what can we do? It seemed like everything that made Roulette successful on the back end, not only was it ineffective on mobile, it was actually a liability. So what could we do? Well, remember when I talked at the beginning about how we had to turn the system on its head to make it work for mobile? Well, that's where this happens. We ended up re-centralizing all of the logic. Instead of having smart clients at the edge, we had dumb clients, and we centralized all the assignment logic in a back-end service. So let's talk a little bit about why that was a reasonable thing to do. So for one, the bandwidth usage. So an evaluation object, which is the data structure that's produced by computing a variant assignment, is much smaller than an experiment definition. Not only that, it has an incredibly regular structure, which means it compresses beautifully. Like, we usually see maybe 95% or more bandwidth savings when we enable compression. So that's great. Saves our customers some money. This is less mobile specific, but this has the additional benefit of keeping the number of SDKs that we have to a minimum. So remember that I showed you we have 3 back-end SDKs. Each one implements its own copy of the assignment evaluation algorithm, which is quite complex. Keeping these 3 in sync is a tremendous amount of work, because if they get out of sync, typically the result has been subtle bugs that take a long time to discover, cause a lot of damage until they're fixed. This also has the additional benefit of helping with availability. So this is really kind of the key problem for mobile experimentation systems, bandwidth aside. Operating conditions for mobile applications are just so diverse. Like, you really can't make many assumptions about the environment your apps are going to be used in. Particularly, you can't assume good or even any network access. Well, we can't eliminate the need for network access, but we can minimize it by saving the assignments to disk. It sounds simple, and it is simple, but it worked. So on Android, we use SQLite, which was a dream. It makes inserting and querying for your assignments super easy. Even that might have been overkill, though, because our iOS team just decided to dump the whole blob to disk and read it out when they needed to. It worked. So this fixed the availability problem, but introduced a bit of a race condition. So the first time you start up an app, after installing it, you have absolutely no experimentation data whatsoever. And I hope it's clear at this point in the industry that blocking app startup by fetching multiple megabytes of data from a remote server, it's not a great thing to do. In fact, it's something to avoid at all costs if possible. Well, we didn't really solve that problem. We hacked around it. If the app needs an experiment assignment before it has the data, we just assume that it's in a controlled variant and call it a day. We do save that override locally so that we have a consistent user experience, but it works. And it also has the nice effect of solving the memory issue. Since we're saving things to disk and reading them out as needed, we don't need to keep all that data resident in memory. So that memory is available for the application to use for actually useful things. And with that, that brings us up to today. So it's not all sunshine and roses. Although Roulette serves us very well at scale, there's a lot more work to do. I think one of the biggest problems that we have to solve right now is the API that we expose to people. The Roulette architecture itself is fairly simple, but the data structure is quite complicated, and exposing it in an API has been challenging. The problem is that because experiment definitions are so flexible, you have all those rules that can require different bits of input about a user, developers really have no way of knowing ahead of time what input they need to provide. So it's very easy to have a misconfigured experiment. I think what we need to do is find out some kind of opinionated APIs that give safeguards. Some of our teams have built those opinionated APIs for their own environments where it works for them. I think if we want to make people successful, that we need to really think about how we approach this kind of problem in a different way. I think maybe code generation would be a really great solution here. Like, you have all these experiment definitions, so just generate a strongly typed API that people can use with confidence, or maybe even delete the backend and just check all your experiment definitions into Git and code gen off of that. Probably won't do that just for the operational overhead. Like, nobody wants to wait for CI for their experiment toggle to take effect. But we're still thinking about this. I've talked a little bit about how having multiple different SDKs is just a lot of opportunity for subtle bugs. We'd love to consolidate this into a single code base. And there's a lot of good options nowadays. We could write something in Rust or in Kotlin native, or even, honestly, even C++ would be a tremendous improvement. We haven't done this yet just for resource constraints, but I would love the peace of mind this would bring. And I think finally, the last important thing we want to do here is reevaluate our decision to use polling everywhere. It's worked, but it is inefficient. I'd love to take advantage of Firebase or APNS to push updates out to our mobile clients. I would love to do something similar on the back end, like set up RabbitMQ or something to fan out updates to all of our back-end nodes. That would be awesome. But that's to be determined in the future. And with that, I want to say thank you. At this point, I've talked about how Instacart developed the ability to run tens of thousands of experiments with billions of evaluations every day. I've talked a bit about how it works on the back end, and I've talked about how what makes things work on the back end doesn't necessarily translate to mobile and how you have to reconsider. I've talked a little bit about how a small amount of computer science can have a tremendous impact and how even more of our problems are just solved with duct tape and glue, and that's fine. So I hope that I'm leaving you with some ideas for your next system design, or at the very least, with some problems that you'll know how to avoid before you encounter them. And with that, I just want to say thank you for spending your time with me. It's been a pleasure.